in order to transition from linear homogeneous systems to nonlinear systems, the first step would be to consider a linear but a non-homogeneous system, right? So it is linear, the coefficients are constant, but it is not homogeneous, and the non-homogeneity is also a constant vector. So recall that we already saw that this system, it describes the flow of liquids via 3 interconnected tanks. But what I want to do now is to find equilibrium solutions. I'm going to solve this system, but the first thing that I'm going to do is to find equilibrium solutions. And in order to do it, I need to equate my right-hand side of the system to 0, because the left-hand side of the system tells me that dx dt is 0, and if the and then if dx dt is 0, it means that x itself is a constant. So then by doing this, we are going to obtain constant solutions. And this is just an algebraic linear system of equations that you can solve directly. Maybe I'll just mention that if the matrix of this system, which is this matrix, is A, then the solution is, of course, going to be A inverse times negative 300, negative 150, and 0. Well, then we're going to do a very clever trick. So we're going to make a substitution. We will introduce new variables, y1, y2, y3, instead of the old variables x1, x2, x3. So the old variable x is changed to the new variable y. And then we're going to see how the system of differential equation changes. So first, of course, the only thing that we are doing is translating the vector. And of course, if you add a constant to a vector, then its derivative doesn't change. So which means dy dt equals dx dt. So this thing is just dy dt. What is the right-hand side? So notice that in the right-hand side we have our system of differential equations, A, times our vector y1, y2, y3, plus A times this vector 9203, well, something, but recall that this vector was actually A inverse times minus 300 minus 150, 0, and plus 300, 150, 0. Well, but then of course A times A inverse, they cancel out. Minus 300 plus 300 is 0, so this disappears. And the only thing that remains is our original matrix A times the unknown vector. So which means by doing this substitution, we transformed a non-homogeneous system to a homogeneous system. And of course, we did it for a specific example, but I even wrote it with a generic matrix A. So of course, it is going to be always like this if you have a nonlinear homogeneous system of the type dx dt equals ax plus b. And so if you calculate the equilibrium solution, which is A inverse times minus b, and if you apply a similar substitution, then you're going to transform the non-homogeneous system to a homogeneous system. Well, but then to understand stability, we need to figure out whether eigenvalues are positive or negative. So a system is asymptotically stable if and only if all the roots of all the eigenvalues have negative real part. And for this, we have the so-called Routh Horowitz theorem. So let me highlight it. This Routh-Horowitz theorem is a theorem which tells you exactly how you can just look at a polynomial and figure out whether all its roots have negative real part or whether it is not true. You can Google it up. I don't want to go into details. So let me just tell you that for a cubic polynomial, we would have to do this. That's the only thing. And if the product of this and this is bigger than the product of this and this, then it is true. Then all the roots have negative real part, and the equilibrium is actually asymptotically stable. So for those of you who like a little bit of a challenge, I suggest that you try to think about it. So prove the following things. If you have a monic polynomial, which means its leading coefficient is 1, with real coefficients, right? So then, if the real part of every root is negative, then all coefficients of the polynomial have to be positive. If additionally you know that all roots are real and coefficients are positive, then all roots are negative. But it is possible to construct a specific polynomial with all strictly positive coefficients, but some of its roots have positive real parts. So they're complex, but have positive real parts. So please try to think about it and try to come up with a specific example. Well, anyway, so then if you want to calculate the actual eigenvalues, you can do it. All of them are negative, so which means that the equilibrium here is some kind of a three-dimensional version of a nodal sink. So all in the neighborhood of the equilibrium, all solutions approach the equilibrium, and here is the specific solution, right? So as t approaches infinity, everything flows towards the equilibrium. The only difference is that the equilibrium itself is not the origin, but rather this point, which means that as time goes by, the level of sugar in the first tank is going to approach this number, the level of sugar in the second tank is going to approach this number, and this number in the third tank. Okay, so that's